Okay, so it's 3 o'clock. So welcome to AIP Open Seminar. So here are some important notices about this seminar. So first, reproduction is prohibited. So 複製を禁止します。Number two, reproducing all or any part of the content is also prohibited without the author's permission. 所有者の許可なくコンテンツまたはその一部を転載することを禁じます。Third is this seminar will be recorded and video will be available on the American AIP website later. And if you have any questions or comments, please scroll to the bottom of the page and click the Q&A tab. You can put questions or comments in the box. 質問は画面下部の Q&A 機能をご利用くださいということです。Okay, so good afternoon, everybody. Welcome to Riken AIP Open Seminar. And today's topics are from Machine Intelligence for Medical Engineering Team. I'm Tatsuya Harada, the team leader of Machine Intelligence for Medical Engineering Team. I'm also a professor at the University of Tokyo and National Institute of Informatics. So I'd like to talk about the overview of machine intelligence for medical engineering team. So the goal of our team is to invest the intelligence systems to assist medical diagnosis and treatment using machine learning. A doctor uses various devices to observe patients. For example, endoscopes and CT and MRI are used. So in addition, there is medical record information, which includes medical interviews with patients. So our team's goal is to develop a system using the predictive model that can detect lesions, extract body structures, and determine the benign and malignant conditions based on this multi-modal information. So this slide shows our team's concrete efforts to achieve this goal. The first topic is intelligence support system for diagnosis of heart disease. This will be explained in later slide. Cardiac disease is the second leading cause of death in Japan. And we believe that it will be beneficial to develop a machine learning based method to assist in the diagnosis of cardiac disease. The second topic is cloud infrastructure and AI image analysis to promote the utilization of medical big data. This is a medical big data project of NII, so which is being carried out in collaboration with various medical societies. So I'm also the vice director of this project at NII, and my team at Riken AIP is also joining in this project. Cross-san will present the details of this project later, so but I will give you an overview of this project. The third topic is research on the general machine learning methods for medical data. So in addition to research for direct medical applications, we are also developing general machine learning methods that can be used for medical data. So invariant and feature extraction will be explained by Mukta-san, and the interpretability of CNN will be presented by Lee-san later. So from here, so I will give a brief overview of the three topics. The first, I will give you an overview of intelligence support system for diagnosis of heart disease. So cardiovascular disease is the second leading cause of death in Japan. And cancer is a leading cause of death, and cerebrovascular disease is a third. However, since cancer includes various organs, such as lungs and stomachs, the heart may be the leading cause of death when viewed as a single organ. So in terms of the number of patients, heart disease is second behind cancer, but has almost the same number of patients. The average medical expenses are about 1 million yen, so each for stomach cancer, colon cancer, and rectal cancer, and about 1.7 million yen for heart disease. So from this figure, so we can see that the cost of treatment for heart disease is very expensive. So we are working on this research because it is essential to build an intelligent system to assist in the diagnosis of heart disease in terms of mortality, patients' numbers, and medical costs. So in order to build an intelligent system that supports the diagnosis of heart disease by machine learning, data is super important. So therefore, with the cooperation of Sakurabashi Watanabe Hospital in Osaka, thanks to the Koyama Sensei, we have constructed a cloud system that collects a vast amount of data related to heart disease and started a full-scale operation last year. As for the medical imaging data, we have collected about 15,000 CCTA images, and this number is now increasing. This data includes ECG data. Currently, so we are conducting manual segmentation and annotation with risk scores as supervised data. As for medical records, we have collected about 68,000 structured data and about 15,000 unstructured data, such as medical interview information. Using this vast amount of data, we are conducting research to get models that support the diagnosis of heart disease through machine learning. So final goal of this topic is to build a comprehensive diagnosis and treatment support system for cardiac disease based on the quantification of cardiac functions using multimodal information. So we are currently working on the construction of each module of the coronary artery disease risk estimation. Specifically, so the path of the coronary artery is estimated from the 3D volume data obtained from CT. From the estimated path, the system infers the outer and the inner boundaries, so extract the calcified and non-calcified plaque, and predicts and visualizes the risk of heart disease. So this slide shows the results of the automatically estimates the risk of coronary arteries. Results have been presented at the medical information conference, such as MICAI. More detailed information may be provided by Cross-san later presentation. So next, I would like to briefly introduce the AMED project of NII. So as mentioned earlier, so I am a Vice Director of Research Center for Medical Big Data at NII, and I was also participating in AMED ICT infrastructure establishment and implementation of AI for clinical and medical research as a member of working AIP team. So this is a huge project, and the goal is to collaborate with 7 medical societies to collect the data in a cloud where machine learning can be used to build useful models for medical diagnosis. The 7 medical societies are the Japanese Society of Pathology, Japan Radiological Society, Japan Gastroenterological Endoscopy Society, Japan Ophthalmological Society, the Japanese Dermatological Association, the Japan Society of Ultrasonics in Medicine, and the Japan Association for Medical Informatics. So NII, so University of Tokyo, so Nagoya University, NICE, the Kyushu University, Chukyo University, Tokyo University of Agriculture and Technology, the major university, Nagoya Institute of Technology, and RIKEN are participating as an information analysis team. And actually, this project finished last fiscal year, but the collaboration with some societies still continue. So we will briefly introduce some results in this project. The first one is pathological diagnosis. The results were obtained in collaboration with the Japanese Society of Pathology. Thanks for the Abe sensei, Fukuyama sensei, Yoshida sensei, and Kitaka sensei. The image used for the pathological diagnosis is a huge image of more than 10,000 by 10,000 pixels. So in order to determine benign and malignant regions in such a huge images and segment them, computation is very difficult due to the shortage of the memory. To solve this problem, so we have developed a memory efficient and high accurate image segmentation methods. The second one is detection of lesions in endoscopic images. The results were obtained in collaboration with Japan Gastroenterological Endoscopy Society. Thank you for Tanaka sensei. So in general, there are only a small number of images with lesions and a large number of images without lesions. Therefore, it is necessary to solve the imbalance problem between images with lesions and images without lesions. To solve this problem, we have developed a method to automatically generate images with lesions by combining lesion areas with normal images, thereby improving the performance of lesion detection. So we've studied a lot of machine learning methods which are applicable to medical information processing. This slide shows some example of machine learning method for medical data. The first one is invariant feature extraction. Mukta-san will explain this topic later. The others are non-rigid object tracking and reconstruction, novel deep neural networks for hierarchical data, knowledge transfer, and interpretability of the convolution neural network. So Lin-san will explain the learning from data for medical information and the interpretability of convolution neural network later. So here I will introduce non-rigid object tracking and reconstruction, novel deep neural networks for hierarchical data, and knowledge transfer in short. So the target of medical treatment is human, okay? And the human body is not rigid, but non-rigid. So therefore, tracking and reconstruction of non-rigid object is considered to be one of the most important issues. So actually, the tracking and reconstruction of rigid bodies has been actively studied in the field of robotics, for example, in self-driving. However, the tracking and reconstruction of non-rigid objects is still an open problem. So our team, Lee-san, developed a method for robust tracking of non-rigid object, even when large deformations occur between the source and the target frames. This slide shows the results of the first time that both non-rigid and rigid objects are tracked and reconstructed at the same time. So these movies show our results. As you can see, the tracking and the reconstruction of the not only the rigid object, but also the non-rigid objects are well performed. So there is a lot of knowledge used in medical information processing that is represented by three structures. Most conventional neural networks assumes Euclidean space, but processing in Euclidean space is not always optimal. So for example, it is known that efficient one-to-back can be achieved with fewer dimensions by using the Poincare embedding for hierarchical data, hierarchical structure. So thus, by using the hyperbolic geometry, so we can expect to realize the best neural networks for data with hierarchical structure. So therefore, our team, so Shimizu-kun, constructed new neural networks called hyperbolic neural networks plus. So we believe this is a new direction for non-Euclidean neural networks. So the training models using medical data is often faced with a domain gap. So for example, a model trained on data from manufacturer A's measurement devices may not be useful for predicting data from manufacturer B's measurement devices. In addition, staining method of hospital A is different from that of hospital B. So a model trained on the data from hospital A may not be useful for hospital B. The goal of the domain adaptation is transfer knowledge from source to target domain with a domain gap and to run a classifier that works well on the target domain. So in unsupervised domain adaptation, so labeled examples are given only in the source domain, and there are no labels in the target domain. So therefore, the unsupervised domain adaptation is very useful for medical data where there is a domain gap and a huge annotation cost. Our research team has proposed various methods for the domain adaptation. For example, we are developing a domain adaptation method for cases where the target data contains categories that did not exist in the source domain. So we are also developing a domain adaptation method that can be used for the object detection. Recently, so we have been developing the unsupervised domain adaptation for situations where source data is not available. Since medical data is often not made public due to privacy issues, so we believe that source data-free domain adaptation is an attractive approach for medical information processing. Okay, so this is last slide on my part. So I'd like to introduce today's speakers. First speaker is me, and my talk is about the overview of my team. The second speaker is Mukta-san. The title of his talk is Invariant Feature Coding Using Tensor Product Representation. So this topic is a very basic method in the machine learning field, but it is very useful also useful for the medical information processing. The third speaker is Lin-san. The title of his talk is Limited Data and Interpretability, the Challenge and the Solution for Real-World Medical AI. And the fourth speaker is Kurose-san. Title of his talk is Machine Learning for Medical Image Diagnosis. Okay, so this is an overview of our team. Thank you for listening. Okay, so I'd like to move on to the main part of today's seminar. Okay, so there is some questions. So the time is limited, so I'll answer a few of them. So first question is, what architecture is suitable for the multimodal AI model? Yeah, good question. So yeah, currently, so convolution neural network is usually used for the image processing, and so transformer model is used for the natural language processing task. But transformer is now also effective for the image processing. So the transformer-based model is effective for both the image and text data. So, currently the transformer-based model is, I think, the currently, so best method for the multimodal AI model. But that's just currently. So in future, so the transformer-based model is best. I don't know whether the transformer-based method is best one or not in future. So we are searching for the new neural network, so such as non-Euclidean neural network. So I hope those new models will be the best or a better method than the transform model or so. Okay. Okay, so and okay, so time is limited. So if there are spare time, our presentation, so I will answer the remaining question. So so I'd like to move to the next speaker. The next speaker is Mukta-san. So the title is Invariant Feature Coding using the Tensor product representation. So Mukta-san, よろしくお願いします。
Hello, I'm Yusuke Mukta from the University of Tokyo. Today, I talk about my recent research about invariant feature coding. So first, I briefly describe what is feature coding. Feature coding is mainly used for the image categorization. Image categorization is a task to make the computer output the category of the input image. And to obtain high recognition accuracy, it is important to run the good image feature representation. Let us review the traditional image recognition pipeline. In this pipeline, the input image is regarded as a bug of local information and use the distribution information of the input bug as a source of the categorization. To this end, we first densely sample the local feature from the input image into local feature space and model the distribution of the local features in the local feature space using some parametric probabilistic model, and then use the model parameter as a global feature. And we finally apply some classifier to output the category of the input image. One example of such local feature is shift. Shift assumes that edge information is important for categorization, and then first split the input local region into 4 times 4 subblocks, and then calculate in each local block the image gradient with respect to 8 direction. Then use the 8 times 4 times 4 equals 128 dimensional feature as a local feature. One example of the feature coding is bug of visual words. Bug of visual words first applies k-means clustering on the local feature space, and then calculates the histogram of local features assigned to each local clusters. Then calculate this to use the global feature. Another example is generalized linear correlation. This global feature regards the input image distribution using Gaussian distribution and use the average and covariance information for the global feature. Currently, feature coding is mainly combined with the CNN convolutional neural networks to enhance the performance of convolutional neural networks. Convolutional layer is a layer that densely applies the same filter to the input subregion. Therefore, we can regard the output of the convolutional layer as a bag of local informations. For example, when we obtain the local feature, when we obtain the output with F filters with H height and with W, then we can regard this as a set of H times W local features with its dimension F. One related work that uses CNN as a local feature is a deep filter banks. Deep filter banks applies the convolutional neural network local features, which is pre-trained by the ImageNet plus Fisher vector. That models the local feature distribution using Gaussian mixture model and use the parameter for each Gaussian list as the global feature. On the texture recognition dataset, as we can see from this slide, texture image has much different property than the standard image categorization dataset, such as ImageNet, and we can expect that simple fine-tuning doesn't work well. And here is the result where IFV means shift plus Fisher vector. VGG means a VGG architecture, which is a CNN. And FC means fine-tuning. FV means Fisher vector. And from this table, we can see that using CNN local fits shows better accuracy than using SIFT. And also, we can get better performance using Fisher vector than simple fine-tuning. Another example is a bilinear CNN that uses a bilinear product of the output of two input CNN local feature as a global feature. Since bilinear pooling that uses a multiplication of two input can be calculated by simple matrix product. We can calculate the backpropagation easily. Then we can run the full model in an end-to-end manner. Further, we often use the same model for this A and B. In this case, bilinear pooling comes down to simple bilinear product. And here is the result, where FV shift means FV Fisher vector plus shift. XCNN means fine-tuning of CNN. And FVCNN is a Fisher vector plus CNN, describing the previous related work. And BCNN is a bilinear CNN. And this WFT and WFT means we fine-tune the full model, or we only run the final linear layer. And from this result, we can see that bilinear CNN shows better accuracy than fine-tuning and Fisher vector. And also, fine-tuning for the model contributes to the performance. Aside from feature coding, the important topic for the image categorization is invariance. Many real-world recognition tasks, including image, has several invariants. For example, this is an image of the dog. And even when we apply horizontal flipping or rotation to this image, the image, the object in the image is still dog. Further, this is a pathological image obtained from lymph node sections. And since we can assume that there is no standard direction for this sort of image, and therefore it is natural to consider the categorization, which is robust to image rotation. And so to conduct a categorization that is invariant to such transformations, we can expect it's natural that the obtained image feature is robust to such image transformations. It means that even when we apply horizontal flipping or rotation to the input image, the output feature should be same. So the difficulty in considering invariance for the deep neural network model is that since the DNA applies multiple nonlinear transformations, it is difficult to calculate the invariant information from the output. Even when the transformation applies simply on the input image, after the several nonlinear activation, it acts very complex on the output feature Y. And to construct a DNA architecture that is invariant to such transformation, one solution is to consider the effect of the transformation layer by layer. Here, invariant neural network is a network that consists of multiple equivariant layers, one invariant layer, and last fully connected layer. Given the transformation T that preserves image information, equivariant layer F is a layer that commutes with the transformation, meaning that when we first apply transformation and then apply a layer, the output is the same as first we apply F and then apply the transformation. Then by applying equivalent layer several times, the effect of transformation can be preserved to the output of the layer. Then we apply one invariant layer. Invariant layer F is a layer that satisfies when we first apply T and then calculate F, the output is the same as we simply apply F. This means we remove the effect of transformation. Then the output feature is invariant under the transformation. One famous research for such invariant neural network is group equivariant CNN. Group equivariant CNN first applies all the transformations to the convolutional filter and then apply for the convolutional filter to the image. Then the output of the convolutional layer on the transformed input can be calculated as a permutation between the filter responses. Therefore, the layer becomes equivariant. Then we can use group equivariance, group convolution, and standard convolution to make equivariant layers. But to my knowledge, this model does not consider much about the invariant feature layer. So based on the concept of invariant neural networks, we set our goal to first regard the local feature, equivariant local feature, such as the output of group equivariant CNN or SIFT as an equivariant layer, and construct an invariant feature coding layer that extends the existing feature coding method to the invariant one, and regard the full pipeline as the invariant neural networks. So the difficulty in this case is that since the feature coding function is a complex nonlinear function, it is difficult to calculate the effect of transformations on this global feature. For example, BLAD, vector of locally aggregated descriptors, first splits the local feature space using k-means clustering, and then use the summation of the difference between local features to the assigned nearest neighbor code word as a global feature. Then when we apply some transformation to the input xm, both the xm itself and the assigned code word is changing. So it is difficult to consider both effect. The idea to compute the global feature, nonlinear feature, that the nonlinear feature but the transformation affects simply. We use a tensor product representation. Tensor product is a vector that uses the multiplication of each input elements as its element. For example, when the x is x1, x2, and y is y1, y2, x tensor product y is a vector that x1, y1, x1, y2, x2, y1, and x2, y2. The important thing is that this x tensor product y is a nonlinear function of x and y because it uses multiplication. But the effect, the transformation t tensor product s acts linearly on this input x tensor product y. So we can simply calculate the nonlinear part, the invariant part, using the average of for the transformation. So it is known that when the considered transformation T's form a compact group, we can decompose the effect of T into a pre-calculated basic set of transformations, such as irreducible representation. So we can calculate the invariant feature part of such tensor product using the fixed tensor product between the irreducible representations. And this procedure can be pre-computed before training. Now we move to bilinear pooling. Bilinear pooling is a method that uses a self-second order product as a global feature. From the viewpoint of tensor product representation, this can be straightforwardly regarded as a tensor product between self xt and xt. Therefore, we can extend this to invariant bilinear pooling by calculating the invariant feature described in the previous slide. And we move to BRAD. From the view of tensor product, BRAD that lines up the different vector for each code word mu can be regarded as a tensor product between the difference vector xm minus mu c and the one-of-k representation 1 mu xm, which is a vector that outputs 1 for the index corresponds to the nearest code word c and 0 otherwise. But in general, the effect of transformation on this 1-k vector 1 mu x is not consistent under the transformation. For example, when in the figure left below, when we consider the flipping with respect to y-axis, the nearest code word for the upper green circle does not change, but the nearest neighbor code word for the below green circle changes. So it is not consistent. To solve this, we pre-run the code words so that the set of code words is invariant under transformation. So we propose an invariant k-means that first randomly initialize the code words so that equivariant, and then assign each training sample to nearest neighbor code word, like the standard k-means, and then calculate the next step of code word using the average of assigned code word, assigned training data, considering the invariance. This procedure can be regarded as a minimization of the sum of training data between the nearest neighbor code word under the restriction of invariance, which is a linear restriction. And then this step can be proved to converge to local minima, as the case of standard k-means. Then we calculate the invariant plot using the invariant code word when we calculate the tensor product between x minus mu c and the 1k representation 1 mu x to obtain the invariant plot. Then we also have the BRAT vector locally aggregated tensors, which uses a second order product around each code word. And since the second order product can be regarded as a tensor product between self, we can simply obtain the invariant feature by training the invariant code word and then calculate the invariant part of x minus mu c tensor plot, x minus mu c tensor plot, and 1 of k representation. So we evaluate the proposed invariant feature using standard image recognition dataset, DTD, FMD, UIUC, and CUB. We use pre-trained group equivalent CNN with VGG architecture. And we use explicit feature map method to augment the local feature dimension to 5043 times 8 dimension. And then we apply bilinear pooling, BRAT, which are non-invariant method, and the proposed invariant extension. As for evaluation, we evaluate the accuracy on test data, and to evaluate the robustness to the transformation, we also evaluate the accuracy on the test data with augmented using the considered transformation with standard training data. And we use P4M group that consists of 90-degree rotation and horizontal flip, which is the same as the original group equivalent CNN paper. And here is the result. The above table is for the standard test data, and the table below is for the augmented test data. And bilinear BRAT is for the non-invariant existing method, and bilinear invrat is for the proposed one. From the above table, we can see the consistent improvement in accuracy over the non-invariant method. So we can see that considering invariance acts well on the feature coding methods. As for bilinear pooling, we not only get the better accuracy, we can reduce the feature dimension from 500 to 5,000 to 80,000. So by considering invariance, we also make a compact feature representation. Further, as for the augmented test accuracy, the proposed method does not reduce the accuracy much, but the non-invariant method decreases the performance. So this suggests that the existing method overfits some transformation-dependent information that does not relate to the image context, while our method can separate the information of contents and the information of transformations. Further, we then apply the method to an end-to-end model using bilinear pooling. We use the ISQRT method, that is improved variant bilinear pooling, which can be also which is also an end-to-end method that shows better performance. And here is the dimension and top 1 error and top 5 error for the ImageNet dataset using ResNet 50 architecture. And ResNet 50 and ResNet 50 org is a error for the standard ResNet 50 and trained with data augmentation using P4M transformation. And P4M ResNet is a group equivariant CNN using P4M architecture. And ISQRT is a bilinear pooling combined with P4M ResNet 50. And P4M ISQRT is an invariant bilinear pooling combined with P4M ResNet 50. And from this table, we can see that first, considering invariance in the group equivariant CNNs contributes to the decrease in error. And also, using bilinear pooling contributes to performance. And further, considering invariant bilinear pooling, we further reduce the top 1 and top 5 error. So invariance is also effective for the end-to-end model. Then we apply a method to more finer rotation. We can approximately construct an equivariant CNN for this sort of rotation using rotating the filter and apply convolution. In this case, the invariant bilinear feature of the 2D discrete rotation can be regarded as a square of the coefficient of discrete Fourier transforms. Then here is a result using ResNet 18 architecture for the ImageNet. And this is a same tendency to the previous result, and our bilinear pooling considers invariance shows the best performance. Finally, we evaluate an end-to-end method on the pathological image dataset. This is obtained from Chameleon 15 challenge. This challenge has a 4-slide image of the lymph node sections with annotation about tumor or normal. We then randomly sample 256 times 256 image patches from this 4-slide, and then apply a classifier whether the image is normal or tumor. For evaluation, we randomly sample 3,000 images per each class, normal and tumor, for training and test. We then pre-train for the model using ImageNet, and then evaluate the accuracy after fine-tuning on this pathological image. And we also have the better performance in this case. And our invariant bilinear pooling shows a little better performance than the baseline methods. And from some theoretical viewpoint, we can justify the use of invariant feature in some special setting. When we consider the L2 regularized convex loss minimization, such as soft margin SVM, we can prove that the weight learned from standard feature, non-invariant feature, using the training data with data augmentation is the same as a weight learned from using invariant feature from the original training data. Therefore, we can also not only reduce the feature dimension, but also we can reduce the necessity of using data augmentation for the training. Here is an illustrative example. When we use two-dimensional feature using the h with respect to x and y axis, the large margin linear classifier for this training data should be like this blue line. But when we consider the horizontal flipping as the invariant transformation, then the large margin classifier that also considers the augmented data should be parallel to x-axis. Therefore, we need not memory the x-axis position. This intuition can be formulated, justified using Jensen's inequality. When we calculate the convex loss from the original sample and flipped sample, then this summation can be lower bounded by the loss function that does not consider x. Therefore, also considering L2 norm, the overall loss is minimized when Wx equals 0. Therefore, we need not the non-invariant feature. Here, we summarize our presentation. We first explain about the feature coding, which is a method that encodes the statistic of the local feature. We then provide a method that exploits the invariance for the feature coding function using tensor product and equivariant code word. And we experimentally demonstrated that the proposed method shows better accuracy than non-invariant counterpart and also robust to such transformations. That's all for my presentation. Thanks for listening.
Okay, so Mukta-san, thank you for your presentation. There are some questions. First question is, what is the aim to use bilinear CNN? What is the aim of to use bilinear CNN?
Yeah, bilinear CNN is said to have the information about some texture or overview style. And also, it is known to show good accuracy with easy implementation.
Okay, so the next one is, what kind of operations are being performed at the point where bilinear CNN is fused?
Fused. Which page?
I don't know. Bilinear pool.
Can you tell me the question again?
What kind of operations are being used at the point where the bilinear CNN are fused or applied?
I think it's a question about implementation.
I don't know how to say.
Yeah, as for the implementation.
What kind of operations before the operation of the bilinear pooling?
Before? Yeah, we can directly apply that bilinear CNN on the, for example, after the layer on the CNN, a convolutional layer.
Okay, so before applying the bilinear CNN, so you apply the rel functions?
Yeah, we simply use the output of some convolutional layer or convolutional layer and rel.
Okay. So the second question is it proposed the architecture for DNN that could learn invariance characteristic end to end? So, okay, so I think this, yeah, Mukta-san, so your invariant CNN can be trained end-to-end?
Yes, for the linear model, I mean, from this experiment, I use end-to-end model.
Okay, thank you. So the third question is, it would be more useful to represent invariance as a probability distribution of the DNA's latent feature vector than as a local shift feature.
To which slide? You know?
So I don't know. So which layer? So my question, so I translate. Which layer the invariance is learned in your method?
Yeah, actually, invariance is the sort of invariance is not learned, but I preset the invariance, and based on this invariance, I construct a model. In this model, whatever the learned parameter, the model should be invariant to the preset transformation.
Okay. So the last question is, why do you keep changing the CNN architectures? So even using ResNet 18, any reason for that?
Yeah, actually,
hey.
The current problem for this sort of group equivalent method is it takes much memory, much GPU memory. So when we consider the transformation, larger final transformation, I need to reduce the size of network architecture to keep it in the GPU memory.
Okay, so
it's a sort of implementation problem.
Okay, thank you for the answering. So Mukta-san, so you can see the Q&A panel, so offline, and I think there is a misunderstanding of my misunderstanding.
Okay.
So please answer directly via the Q&A panel.
Yeah, I think I can make a chat to this Q&A.
Yeah. Also, so there are some questions about my presentation. So I've already answered the questions via Q&A panel. So, okay, so any questions are welcome. And thank you for the audience who asked their questions. Okay, so thank you, Mukta-san.
Yeah, thanks for listening.
Okay, so so let's move on to the next speaker. Next speaker is Lin-san. Okay.
Okay. Hello, everyone. This is Lin from Machine Intelligence for a medical engineering team. And today I would like to discuss about the challenge and solution for real-world medical AI. Okay, first of all, please allow me to give a brief introduction of myself. So my background was actually liberal arts, and I took my PhD degree at the Australian National University. Then I joined the AIP and also the University of Tokyo on the Data Sciences Lab last year's March. And my research field on medical imaging covers several areas, from the liver cancer on the MRI, the chest X-ray, the diabetic retinopathy, and also the breast cancer. And here, but I won't let you waste your time. I have published over 10 papers after joining Riken last year, but I won't waste your time in going through all the details of these papers. So today, I would like to share with you some interesting idea about how to deal with the real world challenge. We know the machine learning intelligent algorithms are supposed to be trained in an ideal circumstances. For example, a variety of images, the abundant and accurate image labels, and the very well-defined metrics, where no one goes all the clear problem setting. But unfortunately, the real world challenge is much more complicated than that. So I have to say, the world is not a fine place, but still, it was worth us fighting for it. Okay, so especially considering the medical imaging analysis, there are two questions. First of all, though we know that the computer vision has achieved great success for well-taken RGB images, thanks to the explosion of image data on the internet. But could this success be replicated in non-ideal scenario? For example, the medical image, because you couldn't assume that the image in the internet will have so many MRI or X-ray images. So this is a problem as how to deal with lack of data. And another question is, the standard computer vision algorithm often fall into the game of the numbers. People are competing for 1% of accuracy or 2% of the accuracy. But does this 1% of accuracy really matter for doctors? I really doubt about that. So this leads to another challenge, the interpretability for the medical AI. Nowadays, most of the solutions have two solutions. One is we use it with a model of the model pre-trained on perfect data. We try to apply it on the target data, either through target augmentation or the transfer learning. Now I think the Mukta Sensei Anada Sensei and Mukta Sensei has introduced much about that. And another solution is to adjust the target data. For example, use better hardware, but of course, it is more expensive. Or convert the data into RGB, which, for example, the X-ray or MRI. Then we have to lose a lot of important and valuable information. So our solution is to boldly go beyond the perfect data, the ideal model. We should adapt the network architecture and adjust the hardware setting simultaneously for the real world challenge. Okay, let's take this one for example. This is our work will be publishing CVPR this year. We introduce a human gaze to elevate the data limitation. First of all, we have to, what is a human gaze? So when recognizing the unseen images, human would automatically gaze at regions with certain symptomatic clue. And this gaze can be captured by a gaze tracker, for example, by the token. Then we're thinking, could this help machine learning? Because we know the machine learning has done a lot on the so-called attention model, but all of them are totally machine learning based. Can we have some buyer-inspired or human real gaze-inspired attention model? Then we start from the very challenging and very difficult question. When you're talking about the limited data, what if you even didn't have this data for the training? This is the most challenging one. We call it zero-shot learning. So what is a zero-shot learning? It aims to recognize novel classes by transferring semantic knowledge from seen classes to unseen classes. For example, in the training data, we can have the horse and donkey, and we can know the attribute like what is a horse like. Then from the tiger and hyena, we can know what is a striper. And from penguin and panda, we can know what is black and white. Then give you a textbook. It says, what is the zebra is a horse-like thing with black and white stripes. Then whenever you have a novel image, though even this image is not trained, is not included in the training set, still you can use base your description and imagination to immediately tell, oh, this may be a zebra. So this is how our human is recognizing things and how the zero-shot learning algorithm normally works. So previously in the 2017, a CVPR paper has suggested that using the human gaze as an external input can improve the performance of the zero-shot learning. But their problem is, even in the testing set, they still need this human gaze input. But in the real world classification task or anything, we couldn't wait for the human gaze for that one. Otherwise, we can directly ask that person to do the recognition for us. Instead of waiting for the capture gaze, we're asking, can we directly estimate the gaze to support the zero-shot learning? But of course, this human gaze, the human gaze will be welcome to be collected for the training. Okay, this is our whole pipeline. The first of all, and the most important one, is a so-called gaze estimation model. Let's think, for when you recognize the thing with your some context or knowledge in your memory, you will think, okay, well, give an image. I will at first, what its head looks like. I will try to match its head pattern with my memory and match its wings pattern with your memory. So similarly, when we have this attribute and the image, we use the attention model to try to localize the attribute to localize this attribute vector to the specific place in the image. So we call it the localized attribute learning. This is how simulating how human doing. Then just to think that this attention is like our human automatically gaze at different places to find the to do the reasoning. So we can just convert it to this attention to the human gaze map. So with this human gaze map, we can calibrate it with our collected training data of the real human gaze to further improve this attention model. And finally, with this one, we can jointly optimize the localized attribute with a global image feature and then input it into the standard plain zero-shot learning backbone to finally get a better performance. The most important part in here is the attention transition model. I think you must be recognized. So the query we just embed all the attribute word into a query vector, and then also think this as a key, image feature as a key. I think you must recognize this. This is a transformer. This is actually a transformer. So we think that transformer is exactly the perfect tool for us to find this self-attention. And after we get the estimated human gaze, we have to calibrate it with our human real gaze. So we calculate the L1 distance with a Hungary algorithm to match it. And here's our result. As you can see, that our method outperformed in the zero-shot learning, which is a very competitive area. But our our method have achieved the best, almost the best score on most of the data set. And here is also an interesting thing. So you may ask, how accurate is our gaze? Here is the result. Given an image, then we can estimate the gaze. This is the gaze we estimate. We can find, compared to the existing gaze estimation method, our gaze estimation is very accurate. And quantitatively speaking, from the AUC and the NSS, our gaze estimation also achieved the best, performed much better than the other one. So the takeaway message here is, by collecting the human gaze and connecting it to machine attention, will significantly benefit the deep learning. Now, let's consider another question: how to transfer the model knowledge on the non-ideal situation without changing the hardware. So this is our work published in ECCV last year. So we know that the ground truth label itself is noisy. For example, last March, the MIT researchers estimate there are 3.4% of errors across the 10 data sets, well-known data sets. For example, 2019 916 label areas comprise of 6% of ImageNet validation set. So the solution, one of the solutions can be found in the label noise representation learning. And I recommend everyone to read this survey paper on the label noise representation learning. And inspired by this work, we start to reconsider the noise in the one hot label. So for the one hot label, normally each image is given a unique label as here. But this one hot label does not necessarily reflect the real world distribution. Let's take a very simple example. Given an image here, we have two labels. One is called laptop, one is called screen. But for this image, would you call it the screen or would you call it laptop? Similarly, what would you say? I think that for me, I think that both can be right. So we can assume that real distribution for the laptop and screen should be equal. But unfortunately, in the ImageNet, either ImageNet and most of the data set, you couldn't expect it. Normally, they will always give you a one hot labeling. So either I associate with the laptop or the screen. So we think that for the given one hot label, so we call it ground truth, but actually it introduced this label noise compared to the real distribution. And our observation and the most interesting part of our ECCV paper is that we prove that the knowledge distillation actually elevate the knowledge distillation actually elevate this neighbor noise. So for example, one of the solution is called LSD. Then it can just give, how to say, you can say it will give a uniform distribution for all others except this one. And previously, people have found that the relation between the knowledge distillation and the LSD. And now in this paper, we make a further step. We prove that the knowledge distillation, as you can see, they gave a soft label for that from the teacher, is actually try to alleviate this label noise. So please check our paper for the details, for the reference, for the exact proof. And then this another based on this observation, we further find that the L2 norm of the final layer of an image in the classification can reflect the label noise. For example, in here, with a small noise, with a small normal, when the feature is the image feature is with a small L2 norm, you can see that the image is quite simple and with similar angles. It leaves very smaller, fewer explanation. But on the contrary, when for the images with very large norm, then it's much more complicated and leaves more interpretation. So we're considering that. For the knowledge distillation, the most important part is here. They just divide to generate the softmax in the teachers. We have to divide it by a T. But this temperature, we think it actually reflects the average feature. It normally should, in the previously, it represents the average L2, the noise, the level of the neighbor noise. But in the normal standard KD, they will use a unified T to relieve it. But as we show that each image we can roughly estimate its neighbor noise level. So instead of use a unified T, we substitute a specific temperature measured by the L2 norm of the image internal features and use it for the KD into the KD. Through this very simple modification, I think I have to say it's only like 3 or 4 lines of change. Our normalized knowledge distillation has enjoyed a very high performance improvement. As you can see, with our normalized knowledge distillation, our performance get much improved compared to the standard knowledge distillation. The takeaway message here today is the knowledge distillation could be regarded as a method to reduce the impact of noise in one halt label. And by substituting the temperature, our method, by substituting the temperature T with features L2 norm, we can think that we're actually having a specific temperature for each image, rather than a unified one to better handle the label noise. Okay, thank you for listening. Now, when we are dealing with the real world challenge, I think what we discussed have one thing more, one thing left. What is that? We know when the word artificial is introduced in English from Latin artificialias in 15th century, it means that it should be made by man and contrived by human skill. But this is true. We have spent much of effort on making the artificial intelligence. But nowadays, they will have spent so much effort on it. It's already done. The most important things that we normally ignore is it should be made for humans. And that is why the Japanese government has determined social principles of human-centric AI. So in order to boldly go beyond the ideal model, we think that we should not only, apart from adapting the network and adjusting the hardware, we should also accounting for the human beings for the real world challenge. Okay, let me start from this work. So this is our work published in AAAI 2019, and the first author, it was by a fourth-year undergraduate student who completed this work in summer. Yeah, I introduced this work is collaboration with the Xiangya University, Xiangya Hospital, which is one of the top hospital in China. And I introduced this because the journal version is now under review. So I can only share it with you, the conference version. In this paper, we explain how deep learning works from clinic aspect, not from our machine learning researchers aspect, but from the clinic's aspect, the doctor thing. We try to link the doctors and AI for mutual understanding. So first of all, we start from the cost postulate. The cost postulate is the standard and the foundation for the evidence-based medicine, or you can just assume you can regard it as the modern Western medicine to determine the pathogen and some disease. So for the doctors, we know that the pathogen is invisible and among millions of the bacteria, organs, and things. And for the doctors, it's important to determine the disease from observe the symptoms. And think of this methodology. We also want to do that. We at first to prove that to interpret how deep learning works, we just find the neural. We try to link the neural activation among millions of neurons to the lesions and observe the symptoms rather than a simple number like say 1, 2, or 3, or this disease or not. Okay, please allow me to first introduce the cost postulate. It establishes a link between pathogen and disease. For example, whenever we observe an yield animal, we'll at first isolate potential pathogen and then introduce these pathogens into the healthy animals. So if this animal doesn't show any symptom, or he just or show some other symptoms, we know that this isolated pathogen is not directly related to this disease. But if the animal suffer exactly the same symptom, then from the cause postulate, we can determine this pathogen is related to this disease by via the bridge of the symptom. And similar to this cause postulate, we set things called similar to a Turing test to interpret the classification algorithm. Specifically, we isolate thousands of neurons out of millions of parameters in the deep learning classification method. And we think that those neurons, we want to prove that that thousands of neurons would be directly related to the final prediction. We call that one and encode that one as a thing called pathology descriptor. Then this is like the isolating the pathogens. And then we inject the descriptors. So how can we inject this descriptor in the deep learning? I think that it's quite straightforward. We do the visualization. Basically, specifically, for example, with this one, we can synthesize. We just use a vessel mask, binary vessel bound mask, which only shows the vessel, and try to regenerate a vivid fundus image. But we think that if according to the cause postulate, if our the descriptor is really related to the disease, and it should show some exactly the same symptom of the DR. And this is our work. We first extract the pathology descriptor and review lesions and symptoms in those pathological descriptors. And finally, the most important, the generated symptoms should be plausible enough to fool the doctors. And we take the DR, for example. For the people who suffer the DR, his founder's image will have the symptom like the microorganism, heart exudate, and the things. And first of all, we define a way to extract this pathology descriptor to encode the lesion feature and activations from the DR detection. Notice that this network is a standard network. The input is a DR image, and the output is only the severity, like the non-DR, the mild DR, severe DR. We didn't know anything about the precision of the lesions, and we didn't know any of the precision or types of lesions. And this extraction is totally automatic. And then we use a GAN-based method to visualize it. So this one is quite standard. I don't think we need to waste time in explaining it. And the important thing is, with only the segmentation and that descriptor, we can generate the synthesized image. And the feedbacks from the doctor says the microaneurysm and the laser sky is very consistent with what they observe. But at that time, they think that our heart exudate is of some artifacts, as can be seen here. But don't worry about that. In our journal version, we have solved this already. And here is the most important thing. We conduct a double-blind test on the licensed ophthalmologist. So this is like a Turing test. We just mix the real image and our generated images together, and then show it to the doctor. We ask them to make the diagnosis based on our image, based on the things they observe. So from the criteria we know, with more and more lesions and microorganism, the image should be diagnosed. The image means that it is more severe. And by manually increase the number of lesions when we generate the image, we find that the doctor on the blood test, double-blind test, also predicts to the diagnosis, consistent diagnosis, saying the severity is also consistent with the number of the lesions. So we think that this is very important, and also the doctor are very confident, are very happy to see this result. They find that when they are fooled, they are very happy because they think that, they believe that what we generate is actually a real and the plausible result symptom for them. So the takeaway message is to explain the deep learning from the clinical aspect can facilitate the medical research and the double understanding very well. And finally, I want to introduce this work. We collaborate with Princeton University, the University of Pennsylvania, and Shanghai Jiao Tong University. As we say, that for the human-centric AI, one of the very important things is the fairness. in this work, we estimate and even improve the fairness with adversarial learning. We know that the fairness and accountability are two essential pillars for the trustworthy artificial intelligence. But unfortunately, deep learning as a black box is very vulnerable to bias in the data. For example, for the bias in the user groups like with sensitive attributes like age or sex, especially lack of interpretation makes it even worse. And then in this work, we simultaneously mitigate the bias, and we can even directly detect the bias in the very beginning with only the image. So we think that this can solve this, not only consider fairness, but also consider the accountability to make sure we don't suffer from, we can just report the bias as early as possible to relieve the discrimination, the impact of discrimination in the medical AI. And as you can see the result here, our method improves the vanilla algorithm on fairness very well. Okay, our final today as a summary, the final message to go from ideal model to real world challenge is, first of all, we have to consider the hardware, the architecture, and the human together. And a slight modification on camera, like saying that using a gaze and brain would improve the performance very well. And finally, compared to making artificial intelligence, it is more important to make AI for human beings. Okay, thank you, everyone.
So Lin-san, thank you for your presentation. Okay, so can you, Lin-san, can you see the
Yeah, I can see that.
panel, so can you answer?
Okay, so I will very quickly answer it, and then I will write it in the detail in the back, to leave it to Kolose-san. So one question is, regarding the zero-shot learning, what mechanism contributes well learning to heterogeneous image simultaneously in order to small volume learning? Is there an optimal learning method? Okay, for this one, I think my answer is for the zero-shot learning, because it is based on the attribute. It's based on the semantic information. So it tries to link the semantic information to the real-world images, which introduce much more information. I think this is a key secret why zero-shot learning works. But of course, in the machine learning team community, they have a lot of other interpretations, but I think that I'm not familiar with that part. And people also ask, what is the latest object detection algorithm as SOTA for specialized medical image analysis? I think this is a very good question because the latest object detection method like the FCOS and YOLO V45 normally doesn't work well for the medical imaging because medical imaging is relatively simple and clean. But so those methods, if in order to use them, you have to do the great modification on those methods. So I would recommend if you do the object detection on the image analyze, you should use some more simpler and some older method. Okay, that's all I think. Thank you.
Thank you, Lin-san. Thank you very much. So please answer the question in detail, so via the Q&A panel.
Sure.
Yeah. Thank you. Okay, so let's move on to the last speaker. So last speaker is Kurose-san, and title of his talk is Machine Learning for Medical Image Diagnosis. So can you start?
Okay, so hello everyone. I'm Yusuke Kurose. I'm the visiting researcher in the medical intelligence for the medical engineering team. So I will talk about the machine learning for the medical image diagnosis. This is today's agenda. First, I will talk about the background in the medical research field. And then I will introduce about our research project. So one is the funding from the A-Medal, and another one is conducted in the AIP. So first, I will talk about the problem in the medical image processing. So the unique feature of the medical data is difficulty in collecting data. Usually, medical data includes the personal information. So we have to remove this information to the research.
On the other hand, we have to submit the document to the institutional review board, and it checks procedure of research from the ethical point of view. It takes so much time to obtain an acceptance. The another problem is that the high annotation cost. So annotation requires the medical knowledge and experience. So the doctor can only annotate the images. And this procedure is very time consuming to obtain a precise annotation. This is also the big problem. The third one is the problems for each department. Especially in the pathological image, that image has the high resolution. So we should, to handle this image, we should separate the images to the small patches, and then the classifier conducted the classifying process. On the other hand, the data imbalance is also the problem. Usually, we can easy to collect the normal images, but the cancer image is not easily to correct. So our research objective is that the development of the medical image processing algorithm for the assisting the medical image diagnosis, for solving the unique problems with the machine learning technique. And this is the final goal, is that to help doctors and contribute to societies. So to tackle these problems, we established and joined the project to achieve it. So I will introduce about our research project. First, I will talk about the AIP project. So this is the structure of the AIP project. In this project, National Institute of Informatics organizes it and establishes a project crowd. The medical society joined it as a medical image provider. This is a unique feature of the project. Currently, 6 medical societies joined this project. The Japan Society of the Pathologies and Endoscopic Societies, Radiological Society, and this is the ophthalmological societies and ultrasonic societies and dermatological societies. On the other hand, for the AI development side, 10 institutes joined, including our 10 institutes joined, including our teams. I will talk about the advantage of joining a medical society. If we can cooperate with the medical societies, we can obtain much more data from societies than when cooperating with some hospitals, few hospitals. Okay, this is the AIP project crowd overviews. The medical societies collect the data from each hospitals, and then they anonymize all the data. And then they sent data to the crowd, AIP project crowd in NII. On the other hand, the AI development researchers access to this crowd, and they conducted the research in this crowd. The analyses are conducted in this secure crowd. This is the unique point of this project. Okay, so I will talk about our tasks. Our task is the 3 departments from the 3 departments. The one is endoscopy, and the second one is the pathology, and the third one is radiology. In this talk, I will introduce some of our results. So first, I will talk about the endoscopic task, task of the endoscopy. I will introduce about the anomaly image generation by GAN. This is presented by Mikai in 2019. So I'll talk about the anomaly image generation by GAN. So usually it is difficult to correct anomaly images that include the disease part compared to the normal images, as I mentioned before. So as a result, our model accuracy became low due to the this imbalance. So in order to tackle this problem, synthetic anomaly image generated by GAN is used to detect the gastric cancer. The bottom figure is the concept. So we use the normal images and anomaly part, and then synthesize these images to get the anomaly images. This is a pipeline of the anomaly image generation. So both normal image and anomaly part input into the generator. It synthesizes both images to generate the anomaly image. In this algorithm, two discriminators are employed. First one is a global discriminator. It works for maintaining the normal part and its consistency. And the second one is a local discriminator. Local discriminator checks the to maintain the anomaly part and the consistency between the local and the global parts. And finally, the algorithm outputs the smooth synthesized anomaly image. So this is the result of the generated image. Left side is the input normal images. The middle one is the input anomaly part. The right side one is the generated image. So please see this here. So this is the anomaly part, and this also the anomaly part here, and the position is the anomaly part is here. So you can understand that the position of the anomalies are controlled in our proposed method. And also you can see the synthesized images are generated smoothly. So this is the result of applying the generated images to our detection method. The upper one is the with generated image. This is the proposed method. The another one is the without generated images. The proposed method can overcome the without generated image in the PRAC. Now the bottom one is the qualitative result. So the green indicates the anomaly part annotated by the doctors, and the method with the generated image can suppress the predicted anomaly part in the method without a generated image like that. It suppresses the red lesion like that. So the effectiveness of the proposed method was demonstrated in this figure. So the next one is I will talk about the pathology. So in this project, the binary classification was performed for each part, which was extracted from the WSI as the first step, because the WSI has the huge resolution, as I mentioned before. So we conducted separating the WSI into each part, the small patches, and then the input to the classifiers, and then we get the heat map like that. So this is the classification result with 996 WSI. So this patient, this WSI with the exposed annotation in the University of Tokyo was obtained from the pathological societies. it can be seen. The left side is the WSI, the low images, and next one is the ground truth annotated by the doctors. This one is 64 patients. We use the 64 patients to train, and the last one is 800 patients to use the training. So it can be seen that the accuracy improved as the training data increases. The final PRAC achieved the 0.958. So we also applied the development model to the network in Fukushima as a double-check system. The shortage of the pathologists was a social problem in the Fukushima. So our developer system was implemented on the network in Fukushima from such a background. The implementation is realized in complete with the Japan Society of the Pathologists. This is the structure of the implementation. First, hospital in Fukushima sends the diagnosis request to the Fukushima Medical University through the data center in the JP8. JP8 means the AI project in the pathological societies. In the data center, the automatic diagnosis system is conducted and send the heat maps to the data centers. And add the heat map to the WSI and send both to the Fukushima Medical Universities. The Fukushima Medical Universities check this WSIs and the generated report, and then also checks the heat maps, and then they also add annotation. And then finally, the hospital in Fukushima can see the report like that. Okay, this implementation is it's featured in the many medias like that in the Mainichi Shimbun, Sankei Shimbun, and Asahi Shimbun, and Yomiuri Shimbun like that. Okay, I'll talk about the in pathological method for the segmentation. So this is the problems. These are the problems on the previous method. So as I talked earlier, the patch-based classification can consider only local features. So, but the doctors can consider both local features and global features. Global means the tissue scale features. Therefore, the considering the global features can make the classifier obtain higher accuracy. However, the four-threaded image has a huge resolution. To tackle this problem, we propose this method. This is the segmentation method for the four-threaded images of this size. First, features extracted from the small patches, and then they are input to the segmentation model. This structure can reduce the memory consumption in GPU, and the segmentation can be realized in the pathological image field. This is the experimental result. The blue one is the previous method results. This also achieved the 96% in the PRAC, but the proposed method overcome the previous method. This achieved the 99%. This is the qualitative result. The left one is the WSI, and this is the next one is the ground truth. And the red one indicates the group 5. And the gray one indicates the group 1. This is normal. The purple one indicates the non-labeled regions. In the previous method, this one, some patches predicted as a cancer around the normal patches like that. But this is very confusing for the doctors, for the pathologists to the diagnosis. But in the result of the proposed method, this misclassification results are suppressed like that. And the accuracy became higher than the previous method. Okay, I will talk about the AIP project. As Hado Sensei introduced these figures, this is our data collection scheme. So we are cooperating with the Sakurabashi Watanabe Hospital in Osaka, and they sent the data to the cloud data center, our original cloud data centers. And then this data center sent the data, all the data to the AIP, and we can access this data, and then we can conduct the research in this in the AIP. So in this presentation, I will introduce our development algorithms in this project. So I will talk about the significant stenosis. Stenosis is the narrowing or blockage of the lumen in the coronary arteries. However, when the narrowing more than 50%, this called a significant stenosis. This is very risky for the patient life. The stenosis is detectable in the coronary computed tomography angiography, but the manual detection is a burden for the radiologist. This is our proposed method part, but these are the pre-processing by the commercial software and manual procedure. We got the 3D CCTA volumes, and then detect the coronary path by the software, commercial softwares, and then the commercial software stretch the the coronary arteries to the straight. We use in this method we use these slices, and then they classify the significant stresses or not. As a proposed method, we employed the CNN feature vector encoding as a feature extractor. This is originally proposed for texture classification. This has the advantage for describing the regions of arbitrary shapes and sizes. The proposed method considers the feature from the multiple views. This concept is similar to the radiologist diagnosis. This is a proposed method. Okay, then we have the multiple networks, but the network's architecture is the same. And first, we extract the feature extraction by the CNN, and then conduct the feature vector encoders, and then the classifier classify the images features, and then they get probabilities. So we also we repeat these procedures, and then we can get the probabilities for the significant stresses. This is the experimental setup. This data set is a non-public data provided by the Sakurabashi Watanabe Hospital. This is the CPR views images. We use 57 patients. 3 arteries per patient is including. In the data set, 70 significant stenosis in total. The annotations from the three experienced experts. This annotation is the binary annotation. 0 means the non-significant stenosis, and 1 is the significant stenosis. This is the data augmentation technique and inverse. This is the result of our proposed method. So, since the dataset annotation and evaluation strategy is different, so only on the indirect comparison is possible. So, yeah, this dataset is changed. In the multi-view ensemble, the achieves the 80% in accuracy. So even though the learning data is about 1/3 of the existing method, it is comparable to the highest accuracy of the related works. This is the quantitative result per view. Each view provides the information on the parts of the artery inaccessible from other views. Using several views at the robustness against the outliers and positives hidden from certain views. With the multi-view ensemble approach, we can increase the classification accuracy without increasing the complexity of the method. Also, we conduct the coronary wall segmentation detection method. So the coronary artery diseases can cause the abnormal artery functions and related diseases. This is usually caused by the arteriosclerosis. Yeah. This is complicated and time-consuming for the diagnosis. So therefore, the coronary wall detection of the coronary artery can help the doctors. In this paper, we propose the algorithm which automatically detects inner and outer boundaries of the coronary artery. This is a proposed method of our method. So the pre-processing is the same as I mentioned before. This one is the changing. We use the 3D encoders and 2D decoders. We also use the input multiple slices. This is for the considering the adjacent slices. And then output one predictions. This is for the reducing the model parameters. As loss function, the weighted Hausdorff distance is employed as a loss function. This is the experimental setup. The 34 patients we used. This is experimental result like that. The matrix is the Hausdorff distance, so the lower is the better. So our proposed method is the highest score in the compared to the another method. This is the cultural evaluation. This one is a proposed method. So the red one is the annotation, and the white one is the inner boundaries predicted, and the white one is the outer boundaries, and blue one is the inner boundaries. So proposed method obtained the best result compared to the others. This one is the last papers I introduced these seminars. So there is still unsolved challenges when plaques and bifurcation exist in the slices like that. So it causes the early termination of the artery and makes a fault. So this has the two types of the solutions during the training and post-processing. But in this research, we focus on the post-processing. We developed the tube beam static search. This method evaluates tube shapes among the boxes of the adjacent slices and finding the most plausible parts of the artery wall. And this is the advantage of the method is that the running a model is not required. Yeah, this is just a post-processing. So this is our method overviews. First, the segmentation results are obtained and then input into the TBSS method. Then it reconstructs the artery wall from the probability maps, and we conducted the contour finding algorithms, like a skeletonization. Finally, we obtained the contour result. The green one indicates the inner artery walls, and red one is the outer artery walls. This is the detail of the proposed method. The segmentation results are input as the probability maps of the slices in an artery section. Okay, this figure shows the way to the search the parse. The algorithm focused on this C1's probabilities. When the probability in C1 is larger than T, the algorithm moves to the next slide. And then if the probability in the C2 is lower than T2, then the process would backtrack. Otherwise, the process would proceed to the next slide. Like that. Okay, the algorithm repeats the procedure. Finally, it obtains the reconstructed result of the inner and outer boundaries. So this is the experiment setup. The 33 CCTA scans we used, and hyperparameters and conversion methods like that. Okay. This is the qualitative results. This one is our proposed method. The blue one is the inner wall predicted by the segmentations here. And the white one is the outer wall. The light green one is indicates the inner contour predicted by the algorithms. The red one indicates also the outer contour. So in the proposed method, there are some noise here like that, but we will try to remove it to improve the accuracy. But in the most cases, only the boundaries of the proposed method can provide across the contours. This is the qualitative results. The method we use the metric as we use the average house stop distance of the old slices as the metrics. TBS is not improved the original segmentations, but also outperformed the comparison methods, especially in the unhealthy slices as they contain image artifacts hard to reconstruct. This is our slide conclusion, my slide conclusion. So I talked about some of the problems on the medical engineering field. To solve this problem, we joined the project and conducted the research. But there are still issues to be solved for the clinical application. We will keep continuing the research and try to contribute to societies. Thank you for listening.
Kristen, thank you for presentation. So there are some questions. So can you see the Q&A panel?
Yes.
So,
yes.
Okay, so for about the first question, so is it possible to control and verify whether the images generated with variations generated by GAN are medically certain?
This means, okay. What is that? Okay.
Yeah, I think it's very hard to
Yeah. It's hard. I think it's hard.
Image by GAN, so which are medically certain. So it's just appearance-based method. So there's no function to appear the symptom. So some disease. So it's I think it's hard to medical research, but it can be generated image can be used for stabilize the line of the lesion detector or the classifier. Okay, so the second question is, did you use SMOT to deal with issue of imbalance cases?
Yes, I have used it before, but the SMOT is it's not effective for the medical images, I think. Yeah.
Why so SMOT is not effective for solving imbalance the medical image?
And the medical image has the very complex to deal with these algorithms, I think. So yeah, SMOT is not effective for the, I don't know how to say, but yeah. But I have tried before, but it is not effective.
Okay, so you try, but experimentally, so experimentally it's not so effective. So in your task. Okay, so third question is, would the proposed method degrade the resolution? So about the 3D encode to the 2D encode.
Yeah, the resolution will be decreased in the first step. We decrease we use the I forgot the number, but I think the very small lesion we used in this method.
Okay, so can you answer the question more in detail? So via the Q&A panel.
Yes.
Okay, Chris-san, thank you for your presentation.
Thank you for listening.
Okay, so all talks finished. Thank you for the audience and joining the discussion. So I'd like to share my screen. Finally, I would like to make an announcement about the schedule of AIP Open Seminars. So you can check the details of the AIP Open Seminar via this link. So here. And attendance to the seminar is free of charge. It's super nice. And but pre-registration is required from doorkeeper to obtain the Zoom access link. Next week, the talks by non-convex learning theory team, Anomaly sensei team, and May 12 talks by the search and parallel computing unit, which is Yoshizue sensei's team, and May 19th talks by the AI safety and reliability units, which is Arai sensei's team, and May 26th talks by the science, technology, and the society team, which is Sakura sensei's team. Okay, so please, if you are interested in these talks, please pre-register via the webpage. So I would like to thank you both the speakers and the audience for providing such an interesting talk and discussions. So this open seminar is now closed. Thank you so much.